Hi, welcome to Zona Mechanica. There is an MCQ on deflection of beam. Figure at the margin indicates the weightage of the question, that is 2 marks. Actually, this is a linked answer type of question. There are two questions based on the same data. The statement for the linked answer questions is like this. A triangular shaped cantilever beam of uniform thickness is shown in the figure. The Young's modulus of the material of the beam is E. A concentrated load P is applied at the free end of the beam. Well, as you can see, this is the beam and a concentrated load is applied at the free end. Okay, this is the fixed end, and this is a triangular shaped beam. Okay, the first question was what is of a section at x distance from the point P, and we got the value of area moment of inertia I is equal to b into x into t cube by 12L. Width of the beam at this fixed end is b, and the thickness of the beam is t. Okay, and the length of the beam is L. Okay, so this is what we got from the previous question. So for the solution of the previous question, you may refer my video as SOM GATE-2011 Q3. Okay, so here you can get the solution of question number 3. Let me show you once. Okay, this was the question number 3, and we got a value of area moment of inertia as bxt cube by 12L. Okay, so now the question number 4 is, that is the second question is, the maximum deflection of the beam is, there are 4 options given. Well, as this is a cantilever beam and a point load is applied at the free end, so the deflection, the maximum deflection will occur at the free end, right? Let me draw once again. Okay, suppose this is the beam. Okay, and after deflection, this is the final position. Okay, so this is the deflection. Let delta be the deflection, so we have to find out this value of delta. So this is the question. Okay, we can solve this question easily in strain energy method. Okay, if we can find out the strain energy stored in the beam, then we can calculate delta easily. Okay, so we have a formula like this. The strain energy stored in the beam U is equal to integration of 0 to L mx square dx by 2 into E into I, where mx is the moment of the force P at xx section, mx. Okay, so clearly mx is equal to P into x, right? P into x, and E and I all are bearing usual meanings. So 0 to L P into x square dx by 2 into E into I. We are putting this value of I, or expression of I, 12 into L. So this will give 0 to L P square, and this 12 and 2, it will give 6, so 6 P square, and this is x square and this is x, so it will give x dx by E into B into t cube, and this L will go up, so L. Okay, so therefore 0 to L 6 P square L by EB t cube. So all these are constants, right? E is constant, B is also width of the beam is constant, T is the thickness which is constant, L is the length of the beam, this is also constant, and P is also constant. So only X is the variable. So if we integrate X dx, it will give x square by 2, right? 0 to L. So I am omitting this integration sign over here. So which will give 3p square L cube, L square and L cube by EBT cube, right? So this is the expression for strain energy stored in the beam. Again, we know the strain energy stored in the beam is nothing but the work done on the beam by the load P for the deflection delta or displacement delta, right? So that work done is half into load into deflection. This is equal to 3 into p square into L cube by EBT cube. So which implies delta is equal to 6p, so 1p will go, and L cube by EBT cube, right? 6pl cube by EBT cube, which is the deflection of the beam or maximum deflection of the beam. So clearly it's matching with option D, 6pl cube by EBT cube, right? So option D is the correct answer. Hope you understood. If you are enjoying, please do share with your friends.